Hi, and welcome to episode 3 of Understanding Motors. So last episode, we discussed how a motor can turn continuously through brushed commutation. This time, we're going to start by addressing a question that many of you may have been wondering. How do we make our motors turn backwards? Starting from a dynamics perspective, this question is easy to answer. If we want to change the direction something is rotating, all we need to do is change the direction of the torque applied to it. But how do we do this practically? As we discussed last time, variables which affect the torque, such as number of turns, magnetic field strength, and motor length and diameter, are all set by the manufacturer and are not practical for the user to adjust, which leaves us with current. Because the torque applied by the motor is directly proportional to the current running through the system, if we flip the sign of the current, we will also change the direction of the torque. In order to switch the direction of current, all we need to do is reverse the polarity of the voltage applied to the brushes, and just like that, we can turn our motor in reverse. However, unplugging your motor leads, swapping them, and plugging them back in isn't a practical solution for basically any application. So instead, we have an electrical system we call an H-bridge that does this for us. A traditional H-bridge uses what are essentially 4 switches to connect a load to a voltage differential in various configurations. These switches are constructed in practice using metal oxide semiconductor field effect transistors, or MOSFETs for short, as well as their gate driving circuits. We aren't going to get into the specifics of these circuits or of the different patterns of silicon dopings used in different types of MOSFETs here, as it's beyond the scope of our current interest. For the purposes of this video series, we will represent these component groups as a set of electrical switches that can be opened and closed quasi-instantaneously via the application of a voltage. One important side note about MOSFETs, however, is that due to their construction, they act like a switch in one direction, but like a diode in the other. Therefore, we will add what is called a body diode to the diagram of each of our 4 switches, which will allow current to flow up the H-bridge at any time. With this H-bridge, if we want to drive current from left to right across the motor, we simply close the upper left and lower right switches. Thus, a positive voltage is applied on the left side of our motor and ground on the right. This will drive a corresponding current and thus a torque. If, on the other hand, we want to drive a current from right to left across the motor, we close the upper right and lower left switches. Again, voltage drives current, current makes torque. An important thing to remember when using an H-bridge is that you never want to close the upper and lower switches on the same side simultaneously. This will result in a short circuit, which is bad news for everyone. While it's not guaranteed to damage your motor, it can certainly damage your electrical components, which can, if not replaced, damage your motor. An additional and equally important benefit of the H-bridge is the ability to modulate the current through the motor. But before we can really talk about that, we have to take a quick look again at the electrical system that is a motor. As we said last episode, a motor can be approximated with reasonable accuracy as a circuit including an inductor, a resistor, and a back EMF-based load. The resistor represents all of the losses in the coil of wire, while the inductor models the energy storage in the magnetic field induced within the coil. Due to the inductor, current running through the system cannot change instantaneously. The voltage across an inductor is proportional to the time rate of change of the current. What this means is that, if the current is changing, the inductor will produce a voltage which will resist that change. So if the external voltage was high, then suddenly switches off, the inductor will produce a voltage in the same direction that the external voltage had been so that the current cannot drop to zero instantly. A useful and accurate physical analogy for those unfamiliar with electronic components would be to compare this inductor to the mass of a very large heavy ball. If we start pushing it with some force, which in this analogy is equivalent to the voltage we apply, the velocity, which is analogous to the current, will not immediately be at its maximum value. In the same way, if we've been pushing it and suddenly we let up and stop pushing this boulder, it won't stop moving immediately. It will smoothly slow down and eventually come to rest. This electrical system responds in the same way as the boulder, just on a much faster timescale. Instead of taking tens of seconds to stop, the current takes small fractions of a second. However, it is notably not instantaneous. Thus, the inductor-resistor circuit acts as a low-pass filter between the voltage we apply and the current that runs through the system. We can take advantage of this current filtering in the motor to control the current running in the system. While the voltage we apply across the leads of the motor are trinary, either being connected to a positive voltage, to ground, or left unconnected, our current will vary over time between 0 and a maximum of V over R amps. And by quickly flipping switches open and closed, we can control this current to specific values within this range. The signal sent to control these switches is called a pulse width modulated signal, or PWM signal. At any point, a PWM signal is either digital low or digital high. The amount of time it spends in each is described by a duty cycle, where a 0% duty cycle corresponds to being digital low at all times, a duty cycle of 100% is purely high, and a 50% duty cycle would correspond with a PWM signal being low for one half of its period and then high for the other half. In order to achieve a smooth current, the frequency of PWM cycles are in the tens to hundreds of thousands of times per second. As a rule of thumb, PWM frequencies are generally set well above 20 kHz to avoid being in the audible range. However, dogs can hear up to 45 kHz, so this should be taken into account to avoid accidentally making an electric dog whistle. During the time when the PWM signal is digital high, the switch receiving the signal will be closed and the current will flow directly through this switch. When a direct current path is not produced by the switches, but current is still being driven due to the inductance of the motor windings, current will then flow up from ground to positive voltage via the diodes. This path can be modified by different patterns of H-bridge switching, and we're going to talk about all of that at length starting around episode 7. Since we now have a structure to control the current to a range of values, we have a way to dictate the torque. And with the ability to control our torque, we now have an idea of how to control the position of our motor. We're going to talk about the systems analysis side of motors and how to perform feedback position control around episode 15, but the H-bridge is fundamental to being able to do this. By utilizing the H-bridge as well as the motor's electrical dynamics, we can now drive a motor bidirectionally and with specific torque. Next episode, we're going to look at what causes motors to fail and how it helped to drive the modern move to brushless motors.